Okay, continuing with the function e to the x, we're going to start off with an application problem right away. Let's say that an object is attached to the end of a spring and its displacement from its equilibrium position is given by the function p of x is equal to 8 times e to the negative t over 2 power times the sine of 4t, where t is measured in seconds and p of x in centimeters. What is the velocity of the object when it first passes through the equilibrium position? Okay, so some prior knowledge, some connections we need to make. Displacement is a position. So p of x is a position function. Velocity is the derivative of the position function. So what we actually need to start doing is take the derivative of p of x. So p prime of x is equal to, now, again, we have one function times another function. So that implies that we need to use the product rule. So the derivative of f, again, it's f prime times g plus f times g prime. So the derivative of f would be 8e to the negative t over 2 power times the derivative of what's inside, which would be negative 1/2. Okay, times the original g function, so the sine of 4t, okay, plus the original f function, so 8e to the negative t over 2 power times g prime. So the derivative of sine of 4t is the cosine of 4t times the derivative of what's inside, which is just 4. Okay, so cleaning this up, so p prime of x, v of x, if we're thinking velocity, right? So v of x is equal to, if you clean up this first term, negative 1/2 times 8 is negative 4 sine of 4t e to the negative t over 2 power. Cleaning up the second term, you get 32 cosine of 4t times e to the negative t over 2 power. You have an e to the negative t over 2 power in both terms. Now, first of all, this should be p of t, not of x. The variables don't match up. That's a goof. Okay, so anyway, v of t. Now, t is time. This doesn't tell us this will tell us the velocity at any given time, but it doesn't tell us what time. So we need to figure out when the object is going through the equilibrium position in the first place. So we need to, this will be our velocity function that we use, but we have to set our position function equal to 0. So kind of off to the side here, we want the position to equal 0. So 8e to the negative t over 2 power times the sine of 4t. And we want to set that equal to 0. Okay, so what we're going to do, we're actually just going to type that into our calculator. Okay, which is what I've done here. I've got 8e to the negative x over 2 power times the sine of 4x. I just hit graph. It's going to give me a bunch of points where it's equal to 0. All right. Obviously, it's going to equal the equilibrium position at 0 because it's starting at 0, but we are looking for this point right here. So to do that, we want to calculate a 0, just, let's say, 0.1 seconds after, up to, since we're in trig mode, that's like a pi over 2. So let's say 2, that's a little too far. Okay, hold on. That's not going to work. So if we calculate the 0 from 0.1 up to, let's say, 1, now we have one point that's above the x-axis, one point that's below the x-axis. It should work. It gives us the point 0.785. Okay, so that's what t is going to equal, 0.785 seconds there. Okay, so that's how long it takes for this object to get to the equilibrium position. And then all we have to do is plug this number into our velocity equation to get the velocity of the object there. So if we just type all of that in, negative 4 sine of 4 times 0.785, close your parentheses, times e, parentheses, to the negative 0.785 divided by 2, close your parentheses, bring it back down, plus 32 times the cosine 4 times 0.785, close your parentheses, times e, parenthesis, negative 0.785 divided by 2, parenthesis. And it tells us that the velocity of this object is negative 21.616 centimeters per second. Okay, so that's a bit of a complicated process there, but that's how we are going to do that. This next part, much easier to do though. Integrating e to the x power. Let's just look at the very basic integral. The integral of e to the x dx. Think about it. What function has a derivative of e to the x? Well, e to the x. So when you take the antiderivative of e to the x power, you get e to the x power. Pretty easy, right? Now it's an indefinite integral, so we have to include our plus c, some arbitrary constant. And that's all there is to it. If it gets a little bit more complicated, let's say x squared times e to the x the third power dx. Well, we can use u substitution with an e function. Let u equal x to the third. So that means that du is equal to 3x squared dx. And again, you see the x squared, you see the dx. So you don't see the 3, so bring that over. So 1/3 du is equal to x squared dx. And then make the substitution. So what we actually have here would be 1/3 e to the u du, the integral of 1/3 e to the u du. Okay, so again, thinking about what has a derivative of e to the u, well, that would just be e to the u power. So you'd have 1/3 e to the u plus c. But again, just substitute it back in. So your final answer would just be 1/3 e to the x to the third plus c. And that's it.